And thank you for coming. I'm very glad to present our results. Our project uses sulfur geochemistry to understand the origin of the moon. And I'm currently a lunar scope postdoc at Brown, working with James Dunting, Alex Evans, and a few other folks in the department. So when we talk about the importance of the sulfur, we need to understand why. So basically, it is largely due to the very diverse geochemical behavior of sulfur. Because it is volatile, it can be influenced by the thermal processing in the disk. And it is also hydrophile that can be affected by lunar co-formation related process. And also it is incompatible, meaning that even in the magma, it can fractionate. So principally, the lunar sulfur and delta sulfur results can trace all of the processes above, making it a very important system to understand the comprehensive evolution history of the moon formation. So basically, if we want to model the lunar sulfur and delta sulfur coevolution properly, we need to account for a sequence of processes during the moon formation, including the initial composition of the disk, and also the high temperature condensation, and also a possible kinetic fractionation in the disk due to volatility-related loss, and also the lunar co-formation, and finally, a potential addition of a late chondritic veneer. So if we want to, again, trace it properly, we need to consider the changes accumulated in each of the stage that I mentioned above. In particular, we found there was an unresolved issue in most of the studies. That is, the lunar co-formation influence was not often coupled correctly with the giant impact models. Let's say in the canonical giant impact model, we have a debris disk, and the debris disk already has pre-existing metal, and that metal is sourced from the impact ejector from the impactor's core. And then the pre-existing metal would re-equilibrate with the lunar silicates to establish the core. That is for the canonical model, but for the high energy giant impact model, that is the synestia, because of the high temperature, pressure, entropy, initial silicate fluid, it is predicted that there's no pre-existing metal in the disk. And the metal only starts to exhaust out of the silicate fluid once the structure cools down. So in that case, the metal exsolution would make the lunar core. So these two very fundamentally different mechanisms for the lunar co-formation would likely lead to distinct lunar sulfur and delta sulfur coevolution that has not been accounted for in previous study, but will be one of the focuses of our study. So we decided to perform a comprehensive modeling, trying to account for everything to understand the lunar sulfur and delta sulfur coevolution under different giant impact models. So our ultimate goal is to see that what is the prediction of the coevolution under different models, and which model can explain what we know about the lunar sulfur constraints the best. So we start from the canonical giant impact. So initially, we need to determine what is the initial composition as a first step. So on all of the following diagrams, the x-axis shows the sulfur concentration in the bulk silicate moon, and the y-axis shows the delta sulfur values. And the ultimate goal is to see after a sequential of the evolution, if the predictions can fall within this box, which is a defined BSM observation. So for the first diagram, we see there's a range of estimates. That is because we can assume some very different values for the pre-impact bodies. And second, it is the high temperature partial condensation effect that would deplete sulfur to the left without changing the delta sulfur much. But then the kinetic volatile loss would further deplete sulfur and increase the delta sulfur significantly due to the kinetic fractionation. And then the fourth column probably is the most important, that is the lunar co-formation mechanism in the canonical model. Because I mentioned that there is pre-existing metal, and sulfur becomes much less hydrophile under the lunar co-formation condition. And then there is an expected sulfur overabundance in the mantle. That's why you see there's a lot of the points that are actually having a larger values compared to BSM. That is very hard to reconcile. So it cannot match even with a final addition of late veneer. So we just couldn't find any match possibly. But if we assume a bigger metal silicate sulfur isotopic fractionation factor, we see it starts to match some better during if we assume the metal silicate equilibration temperature is lower, but yet those matches are rather marginal. So basically the canonical models, yes, it could principally reproduce the lunar constraints, but under very extreme condition with some very restricted parameter space. So what about the synestia model? So similarly, we need to define the initial composition after subtracting the possible effect from the bulk silicate Earth's late veneer. And then like, after the partial condensation, partial vaporization, we still find like a match of a good matches. And the fourth column, again, is very important for the lunar core formation mechanism in the synestia, because there is no pre-existing metal. There won't be any sulfur overabundance. The sulfur would only be depleted if you start to make a lunar core. So that's the difference. That's why you see like we still found remarkable matches between the modeling and the results. And after the late veneer addition, we still found very nice matching. And even if we assume a different sulfur isotopic fractionation factor between the metal and silicate, it still holds true. So basically, synestia model can work regardless of what parameters like you select, making it a very generous, accommodating, and feasible model to explain the moon formation. The next slide, we will see like if we blow up this matching area to see what are the parameter space that can reproduce a successful model. Like we actually see like they are everywhere. Again, it means like synestia model has a very general parameter space to accommodate what we know about the lunar sulfur. And particularly, I don't know if you can see it clearly, it's like the metal silicate equilibration temperature has to be greater than 2300 K. That means it is greater than the solidus of the silicate near the lunar core boundary, meaning that it is very likely for an initially fully molten moon to have been made. And furthermore, our model can still also constrain the disproportional late veneer, which is very interesting. So when you plot our successful modeling for the late veneer to the Earth on the x-axis versus the late veneer to the moon on the y-axis, we see like most of the modeling they fall below the 1-to-1 line, meaning that this has to be a larger late veneer fraction for the Earth compared to the moon, which is consistent with the fact that the Earth has a larger gravity pull and also consistent with some evidence, isotopic evidence such as the tungsten isotopes. And also, our successful model can also constrain how much of the volatile loss can be allowed for the sulfur. So if we plot the sulfur loss due to the partial condensation on the x-axis versus partial vaporization on the y-axis, we can constrain a maximum of 80% of sulfur loss can be solely due to the volatility-related process in the disk. Because sulfur is such a representative volatile species, we can use this result to benchmark the magnitude of the volatile depletion of other species as well, making it a valuable data set to continue to work with. So finally, I'd like to talk about an interesting implication for the lunar metal origin as well. So in the traditional giant impact models, there has to be around a few percent of metal to be ejected into the disk, making the pre-existing metal available, which has been the major constraints in the giant impact dynamic simulations. But our results found that if you eject metal in the disk, it is very unlikely for to match what we know about some of the important constraints from sulfur. So maybe the metal is not a required or even not a allowed component in the disk. So if this is true, it means like perhaps we can open up our ideas to more types of the giant impact models that do not need to eject any metal in the disk. And this can free up a lot of constraints. And maybe we can see if those models can explain better some of the other lunar properties. Perhaps our result could lead to some of the shift in how people see the canonical, the giant impacts to be performed, and see how they should be done in the future. So finally, is our conclusion. So we found that the different lunar core formation, which are tightly associated with the different giant impacts, would make a huge difference in the predicted chemical behavior of a species such as sulfur, which is both hydrophile and volatile. It has not been accounted before, but now we think like this is very important that we should focus more on. And it will apply to many of the other volatile and hydrophile species as well. And our modeling is mostly not consistent with the canonical models, but is more agreed with the synestia model. And metal perhaps is not a required component in the disk. And finally, our results demonstrate the collective contributions of the various post-impact processes in shaping together the volatile and hydrophile evolution. So not a single process would and could explain everything like we know about the lunar observation. And that's my talk. Thanks so much for your attention.